Hello. Hi, I am Michele Thornton. I'm a NASA Earth Data mentor, and Eli asked if I would spend a little time today to introduce you to NASA Earth Data and the NASA Earth Data Cloud. NASA certainly collects a lot of Earth data, and this image shows where a lot of that comes from. This is the NASA Earth fleet, and it shows the history, current and future orbital or satellite missions. Some of you might be familiar with back in the 90s, starting with Landsat and the Terra and Aqua missions, all the way out to present missions, looking at Landsat 9 in the works, Tropics, SWAT, Tempo, if you're familiar with those, and then into the future with Landsat Next and the ESO missions satellites, just to name a few. In that inner swirl, you'll see a lot of the ISS instruments that are active and successful. So a lot of really exciting stuff going on in the orbital category. But not to be outdone, NASA also has a lot of airborne and field measurements and quite an active community there. Airborne, there's active and passive instrumentation. There's in situ measurements that happen. The oceans have ships and buoys and other measurements, and then of course the terrestrial ecology, looking at permafrost, animal movement, and other terrestrial measurements. So quite a bit of activity in through NASA Earth Data. Of course, this all is leading to dramatic increases in data volume and complexity. In 2021, we're sitting at about 62 petabytes. That's grown to current values. So we're up to tens of thousands of data sets, thousands of instruments. And you can see from this graph that will just continue to grow. And it makes sense to move the data that NASA Earth Data holdings are from on-prem storage into a cloud-based storage system. So just a little bit of background, the NASA Earth Data Archive Centers are pictured here. There are 12 of them spread throughout the United States. I work at the Oak Ridge National Laboratory DAC. Our focus is on biogeochemical dynamics and ecological data. That's the data that we get. We actually get a lot of airborne and field data through those missions, but other DACs focus on snow and ice. NSIDC Center in Colorado. There's the Physical Oceanography DAC, or the PODAC, which of course focuses on oceanography. And you can see from that list, there's quite a few DACs spread out, and they're very domain specific. So they're specific to that domain, meaning that data, and also those users. So NASA Earth Data Cloud is a cloud-based archive of its Earth Data observation data. Currently, it's hosted on Amazon Web Services. It's in the US West 2 region of AWS, and all NASA Earth data collections are moving to these AWS cloud archives. A large percentage of data are already there, and the NASA data centers that I just shared will continue to migrate data to the Earth Data Cloud. By migrating data to Earth Data Cloud, this supports a refocus of user data access methods from the traditional download and analyze to data reduction and analysis in place. Instead of downloading data to your particular computer, you're able to analyze data in place in AWS. This allows multidisciplinary, multi-mission science. NASA is able to build a common suite of Earth data tools and services If you're familiar with the DAX, you might find that there are a lot of different tools and services depending on the DAC and the data. So those will become much more common and across data sets. It eases access to data now that data are co-located. NASA Earthdata Cloud is also supporting NASA's TOPS program. That's the Transformation to Open Science. And of course, most of the federal agencies are actively supporting open source science initiatives. So just a little bit about when to cloud, and to start with a note that NASA data will remain free and downloadable. So none of that goes away, and it doesn't always make sense to work in the cloud. It is often the case and will remain available that you can download data to your computer and work with it that way. And sometimes that makes the most sense. But when to cloud, you might think about what data volumes are you working with? Are you working with a large spatial area, or the data are just large and complex because of the way the data are organized? Um, uh, Along with that, you think about how long it takes to download data. Can you store all of that data? Of course, there's a cost for storing data and having that space. Do you have the compute power for processing? These large data volumes often require large memory, and sometimes you hit that wall. So working in the cloud makes sense that way. It might be more efficient to subset and analyze data, especially if they're co-located, if they're from different sensors or different model outputs. Doing that in a cloud resource. If you're working with a team, the cloud can provide a common computing environment. You'll do that today through the OpenScapes environment. And do you need to share data, or is it just an end product? So maybe you can reduce the data and analyze it all in the cloud, and then download and share that end product. So just a few things to consider about when it makes sense to work in the cloud. So this is a little cloud workflow that I borrowed from the NASA OpenScapes area. Simplified it a little bit, but I think it helps to think about the workflow that you might use as you work in the cloud. So first of all, you have to find data, and this is not unique to working in the cloud. We talked about NASA having, 10,000 plus data sets, and step one is figuring out which data that you need. So let me just give you a little example to work with today. This might not be relevant to your particular domain or area of interest, or even today's hackathon, but just to have something. So this is Worldview, and Worldview is this really great visualization application. And this particular story shows atmospheric rivers, and it highlights some data sets that show the atmospheric river that happened during the 2022-23 winter season, when you'll remember California really was hit with a lot of rain and snow because of this precipitation events coming off the ocean. So one of those data sets was the GPM iMerge, and one of the data sets that is highlighted in this Worldview story. And this provides precipitation rate. So as a researcher, you might find this data set or another data set through a NASA application, and it might be relevant to your particular research. And so you want to figure out how to access that data. This is another example in that Worldview application showing snow. But just to focus on that GPM precipitation product, you can go into the Earthdata Search GUI. And in the upper left-hand corner of that GUI, you can put in some keywords and search for that data set. And you can see that I've discovered some collections associated with it. And looking at one, the GPM iMerge final precipitation, level 3, 1 day, 0.1 degree by 0.1 degree data set. And you can see that there's over 8,000 matching granules with that data set. So this is a start. This is a way that a researcher might discover data and discover file naming conventions, formats, and so forth. So traditionally, a researcher might actually start downloading files and granules and then start working on their own compute resource. But this is also sort of the first step at finding data before you start working in the cloud. So just to back up a minute, that was one example of a data set, but remember there are over 11,000 data sets, and all of these are now co-located in Earthdata Cloud. So when you start programmatically accessing these data, it makes sense that each collection is going to have a unique identifier, so that when you start programmatically discovering that data, you can find the exact data set that you want. So those identifiers can include the DOI for that data set. Every data set collection has a unique short name and a unique concept ID, which is just a unique identifier that's assigned to every data set, every collection. So you'll see this in today's tutorial, that you'll use one of those ways of identifying a data set. I just wanted to give you kind of a heads up before you start jumping into the tutorials. That the NASA Earthdata Search GUI can provide you with these unique identifiers. And then looking back at the iMerge precipitation data set that we were looking at a slide before. So if you click on those three little dots and look at the collection details, you'll get another window that pops up, and that window will provide you with a DOI and the short name and a little more searching, and you'll be able to discover the concept ID. So again, that will be demonstrated in the tutorial example, and hopefully this provides you with a little bit of introduction to that. Okay, we found data, we have our unique identifiers. So now let's set up a cloud workspace. There are, of course, several ways to do that, and two are just shared here. The first one is just do it yourself. You can create your own AWS account. You can connect to EC2 instances and then manage your setup and your costs. So, start a virtual machine. If you want to use Python, start that Python environment and start managing the libraries and modules that you want to use. Another way to do this, and what the OpenScapes community provides, is a managed cloud service. And this is a way to really kind of give you a gentle introduction into the cloud. So a company called 2i2c provides a Jupyter Hub environment, in that the images are already provided, and the setup is already the back end of all of that is already provided for you when you fire up a Python instance, for example. And again, this is the way OpenScapes and the NASA mentors work, and often provide workshops and trainings within this managed cloud service. It just takes away so many barriers to getting into the cloud, to give researchers an introduction to working in that environment. So just a little bit more about this solution for access, this OpenScapes 2i2c Cloud. It is a Jupyter Hub application. So the power is that it helps manage multiple user sessions of interactive computing. So you and your colleagues will be able to work in that same Jupyter Hub environment today during the hackathon. Okay, so we found data, we have set up our cloud workspace, and then we can really get into the meat of programming and doing what we need to do with data. So step 4 and 5 here, Eli has probably told you that you're going to need an Earthdata login. And take a break here and get a drink. You're hopefully will be introduced to Earth Access, which is a Python library that helps you navigate through Earthdata login and has a lot of other functionality. And then also provides, you'll see some ways to manage the AWS authentication before you start getting into kind of a typical Python or R type workflow. So a little bit about this Python library for NASA Earth data called Earth Access. There's a website there. If you just Google NASA Earth data, Earth Access, you'll be able to find this. This is a really robust library. It's currently under development, and a lot of new powerful applications are coming out of this. So I just really encourage you to pay attention to Earth Access because it's really simplifying a lot of complicated search and access steps for you. And then once you're into that that Jupyter Hub, the image on the right here shows a hub environment that we just did at AGU last week. So this is working in a Python notebook, and this information is available and on OpenScape's website, and you can look into that after your hackathon today. Oh, and then I'll just leave you with some resources here. The NASA Earth Data Forum is there, and that's a forum in which a lot of subject matter experts are paying attention to. Feel free to go there with any questions that you might have. And otherwise, I wish you the best of luck with your hackathon today. And thanks to Eli for inviting me to give you this overview. Good luck.